sheet attached to your test with a few changes. All right, welcome back everyone. Lecture 12, Math 131. We have this lecture, the next lecture, and then we have test 2 coming up. Today we are going to get caught up on a couple of homework questions, and we're also going to do a little cleanup. I want to come back and hit the chain rule in chapter 3, section 2, because that really gives you a reason why you're taking the derivative of e to the u, where u is a function of x. And that's where I expect test 2 to end, but we'll know for sure after today. All right, so before we started today, I went through and asked this group where some homework questions were. And the first question from the book, and then we'll go to some web-assigned questions, is from chapter 3, section 1. Chapter 3, section 1. Okay, be sure you're working some of the problems from the book. I'm not sure that you get enough drill and practice from web-assigned to make your A pluses. All right, we're in chapter 3, section 1. And this had to do with the product and quotient rules. Product and quotient rules. And actually, the question was for number 33. Let me see if I want to do 32 first. Yep, I think I want to do 32 first. Let's look at 32 together. Okay, I'm on page 221. And number 32 says, find the inflection points on the graph of y equals 1 over x squared plus 1. All right, we've already talked about how you find inflection points, extreme points, etc. And in chapter 3, section 1, we had some new derivative rules. We had the product rule and the quotient rule. So you're still getting the same questions again, but now you have a function that's more interesting, and you're going to have to use a product or a quotient rule. If you just slide up and look at problem number 29, you're writing the equation of a tangent line. Well, we've drilled on that before. To write the equation of a tangent line, you got to have slope, and a slope is a derivative, and then you got to have a point, so you got to get the derivative at that point, and then you can write this equation of the tangent line. So it's the same concepts, but the problems now involve a product or a quotient rule. So question number 32, when you were asked to find an inflection point for a particular function, first thing your brain says is what? I'm going to have to know a second derivative. Because if there is an inflection point, it will be where the second derivative equals 0 or does not exist. Okay? All right, so in number 32, the function is y equals 1 over x squared plus 1. And I know I'm going to have to come up with a second derivative to find the inflection points. All right, how would you go about taking this derivative? There's really 2 different ways you could do it. What do you want to do?
Base it to the -1.
Okay, so one possibility is to rewrite it as x squared plus 1 to the -1, and then use your general power rule. What's another way you could do it? Quotient rule. Bottom times derivative of the top, which would be a 0, minus the top times derivative of the bottom over the bottom squared. So either way is going to be fine. All right, but since you asked to bring it up to a -1, let's just go with that. So the first derivative is going to be -1, rewrite, decrease by 1. What else? Derivative of the inside, which is 2x. All right, so let's just clean that up a little bit. That looks like a -2x times x squared plus 1 to the -2. Okay, -1 times 2x. All right, this is where I would find any possible extreme points, if there are any. And let's just look at it. That's -2x over x squared plus 1 squared. There's no way the denominator will ever be 0 when you got an x squared plus 1. The only thing that makes that derivative equal to 0 is where x is equal to 0. So your possible extreme point is where x is 0, and they drew the picture for you. Where x is 0, that is where you're going to end up having an extreme point. You have a horizontal tangent line. You don't know that it's an extreme point unless you check from increasing to decreasing. Okay? But they drew it for us. All right, everybody good so far? All right, so let's go for the second derivative. What's the notation if I'm doing the dy dx? What's the notation for second derivative? D squared y dx squared. Second derivative of y with respect to x. Now, what rule am I going to have to use here? Product rule, because I have two functions multiplied together. Two functions multiplied together, so I have to go with the product rule. Go ahead of me and then check my work. How'd I do? Okay? All right, well, we know we're going to have to set this equal to 0 for any possible extreme points, but I need to clean it up a lot so I can see what it looks like. Okay, there's a x squared plus 1 to the negative 3, so we're going to put that down in the denominator, make that a cube. And we have negative 2x times negative 2 times 2x, so that must be about, what, 8x squared? Positive 8x squared. Negative 2 times negative 2 is positive 4 times 2 is 8. X times x is x squared. And then the next term is a minus 2 over x squared plus 1 squared. Okay. I'm going to want to set this equal to 0 for possible extreme points. Inflection. Possible inflection points. Okay, what do I need to do here to solve this? Well, don't I need to get this simplified first? Okay, is there any way x squared plus 1 could ever be 0? No, so can I multiply through by the common denominator? It's a rational equation to eliminate the denominators. So because the denominator can never be 0, x squared plus 1 is never 0. All right, I can multiply both sides of the equation by the common denominator, which is x squared plus 1 cubed. Okay, multiply both sides of the equation by this. Okay, I think I'll pick up on some blue paper here so I can keep moving it. All right. Solving a rational equation, that's how we're going to eliminate the denominators. All right, so when I multiply x squared plus 1 cubed times the first term, what do I get? 8x squared. The x squared plus 1 cubes cancel out. When I multiply it times the negative 2, what do I get? Minus 2 times x squared plus 1. Because the x squared plus 1 squared divides out with 2 of them in the numerator, which left me with one more factor of x squared plus 1. And over on the right side, I have 0. All right, so I think we're pretty close now. So we'll distribute here using our distributive property. 8x squared minus 2x squared minus 2 equals 0. We have 6x squared minus 2 equals 0. How do you want to do it? Solve for x squared. 6x squared equals 2. X squared equals 2/6 or 1/3. So what's x equal to? Plus or minus square root of 1/3. Plus or minus square root of 1/3. Okay. So we have two possible inflection points. One where x is negative square root of 1/3, and one where x is positive square root of 1/3. All right, how are we going to determine if these values of x actually are going to give me an inflection point. Yeah, we're going to pick values all around and plug into the second derivative. All right, let's go where the second derivative is easy to look at, right here. You have to go to the second derivative before you started simplifying and changing it around, because this is the problem right here. All right, so an easy one to start with would be x at 0 in the interval where x is 0. So if you put a 0 in for x, what kind of second derivative are you going to get? 0 for x. That whole term right there would be a 0, right? And you get minus 2 over 1. So you're going to get second derivative less than 0, so it's going to be concave down between x at negative 1/3 and square root of positive 1/3. Positive square root of 1/3. All right, now if you put 100 in for x, this first term is going to be pretty big, right? 8 times 100 squared. And the second term is going to be really small because the 100's in the denominator. So that's going to be a second derivative positive. Second derivative greater than 0, concave up. So we know where x is equal to square root of 1/3 is going to be an inflection point. And then pick something less than negative 1/3, such as negative 1,000. But again, you're going to be squaring it, so that's going to be a huge number. Negative 2 over this thing is going to be negative 2 over a huge number. That's going to be real small. So it's going to be positive again, second derivative positive. So it's going to be concave up. All right, so if you look at your graph that they gave us, somewhere in here, which I have no clue where that is, looks like somewhere right in here, somewhere, we're going to have a minus square root of 1/3, and then somewhere right over here, we're going to have a positive square root of 1/3. And so it's going to be concave up until it gets there, then it's concave down, and then concave up again. All right, and then they want the point, so you have to find the y value, which is not going to be too hard to do because you're going to be squaring a square root. So you basically have 1 over 1/3 plus 1. 1 over, you know, when you substitute square root in there, some of you are looking at me like you don't know that. And you have to find the y value. Y is equal to 1 over x squared plus 1. So if we substitute in this, we'll have 1 over minus the square root of 1/3 squared plus 1. 1 over, and if you square the square root, you're going to get the 1/3, and if you square negative, you get a positive. So you have 1 over 4/3, which is what, 3/4? So our points are negative square root of 1/3 and 3/4, and that looks about right because there's 1 up there. And this is square root of 1/3 and 3/4 for the y value. Okay, everybody good? All right, now the question was from number 33. The question I got before class started is find all x such that the derivative is equal to 0, and here's our function. So it's really asking me to find where do we have a horizontal tangent line, where are the possible extreme points, right? As soon as you see a first derivative equals 0, you go horizontal tangent line, possible extreme points. All right, so let's do this one together. My guess is it's probably in the simplifying in order. That's the problem. Okay, the algebra, not the calculus. Algebra will get you. Okay, so here's the problem. Number 33, this is page 222, and we have that y is equal to x squared minus 4 cubed times 2x squared plus 5 raised to the 5th. And we're going to take the derivative and set it equal to 0. All right. Work ahead of me on taking your derivative. What rule are you using? Product rule. Go for it. Okay, will you check my product rule? Is that it? Is that what everybody's getting? First, derivative of the second. You had to use your general power rule, brought the 5 down, rewrote, decreased by 1, derivative of the inside. Plus the second function times the derivative of the first, which was a general power rule. All right, we want to set that equal to 0 so that we can solve for x, and so we need to completely factor. We need to be able to use the rule a times b equal to 0. So we need to, a times b means you've got it written as a product, means it's completely factored. So we must factor completely. Okay? All right, so we're going to use our distributive property in reverse. Distributive property in reverse. All right, basically, let's take care of the numbers first. We see a 5 times 4x, so in the first term we have a 20x, and in the second term we have a 6x. So what's the greatest common factor for 20x and 6x? 2x, right? So we're going to bring on the outside 2x. Okay, if I bring on the outside the 2x, if you want to do it all at the same time, that would leave us inside the big set of parentheses here of what, a 10? Because 2 times 10 is 20. 2x times 10 is 20x. And over here, it will leave me with 3. Everybody got it? Okay, now, in the first term, I see 3 factors of x squared minus 4. In the second term, remember terms are separated by pluses and minuses. In the second term, I see 2 factors of the x squared minus 4. So how many am I going to pull out? 2 of them. Okay, so that means I'm left with 1 factor of x squared minus 4 in my first term inside the big set of parentheses. And I've already taken care of them, all of them in the second term. All right, in the first term I have 4 factors of 2x squared plus 5, and in the last term I have 5 factors of it. So I'm going to pull out 4 factors. All right, and that will leave in the second term here 2x squared plus 5. Okay? All right, so let's clean that up. That's 2x times x squared minus 4 squared times 2x squared plus 5 to the 4th. And when I distribute, I get 10x squared minus 40 plus 6x squared plus 15. Be really careful to distribute. Don't forget your little negative signs there. All right. 2x times x squared minus 4 squared times 2x squared plus 5 to the 4th. And that looks like I have 16x squared. Would that be minus 25? Minus 25. Okay? Everybody good? I think we're completely factored, yes. Well, not really. If you want to completely factor further, that's the difference of 2 squares. 16x squared minus 25 is the difference of 2 squares. So let's do completely factor while we're at it. 2x. Oh, what about that x squared minus 4? Does that factor further? X squared minus 4? X plus 2, x minus 2. So I'm just going to use a little bracket here. X plus 2, x minus 2. Put a little square there. 2x squared plus 5, that's all you can do with it. 2x squared plus 5. And then 16x squared minus 25 factors to what? 4x plus 5, 4x minus 5. Okay, now it's going to be easy to get all the values where the derivative is equal to 0. All right, so we're going to set that equal to 0 because that's what the problem asks us to do. And now all we have to do is read it off. Everybody good with me right here? All right, what makes 2x equal to 0? Okay, x equal to 0. What makes x plus 2 equal to 0? X equals minus 2. What's the next one? X equals positive 2. What's the next one? Nothing from 2x squared plus 5. That can never be 0, right? 2x squared plus 5 under the set of real numbers. All right, and then the next one is x equals negative 5/4, and the next one is x equals 5/4, right? 5/4. Okay? All righty. So if you missed this one, it's probably from the good old days of algebra and factoring, not the calculus concepts. Everybody good? Okay. And before we hit the web assigned questions, I do want to clean up 4.1 because it looks a little scary when it really shouldn't be. Might look a little scary in the exercises. All right. I think that was it from Chapter 3 cleanup. I think so. All right. I'll answer questions again on Monday if that helps. All right. I want you to look at some of the exercises in 4.1 because they look a little scary when you first look at them. And we'll pick, say, problem number 2. All this is really going to do is try to get you to use your properties of exponents. Properties of exponents. It wants you to rewrite 27 to the x as having a base 3, 3 to the kx. And this is just an algebra review. All right, so we will look at page 248. 4.1, we'll just pick number 2. So our goal is to write something with a base 2 or a base 3. So if you have 27 to the x, we need to write it either to a base 2 or a base 3. So we know that 27 is 3 cubed. All right, so I just changed 27 to 3 cubed, now raised to the x. And the property of exponents, when you have a cubed raised to the x, what do you do to those exponents? Multiply. So you got 3 to the 3x. So k is equal to 3. Had a problem, the cube root of 2 raised to the x. Cube root of 2 raised to the x. So we can only have a base 2 or 3, so how would you rewrite cube root of 2? 2 to the 1/3, and you're applying your same property, power of a power, so you get 2 to the x over 3, or 1/3 x. Okay, and the next one was 1/8 to the x. How are you going to write that with base 2 or 3? Okay, 2 raised to the minus 3. You might have to put in a step before that. You might write that as 1 over 2 cubed to the x, and realize you can write that as 2 to a negative 3. So it's 2 to the minus 3x. Okay, so all the exercises, starting in the first part of exercise 4, they're just playing around with all your properties of exponents that you had in your pre-calculus course. Those properties, by the way, are in the middle of page 246. Page 246. When the bases are the same, you add the exponents. When you divide, you subtract the exponents. A product raised to a power is a to the x, b to the x. Negative exponents. It's been hard for you to get this far in the book if you hadn't known some properties of exponents before now. And so it's just kind of reviewing those. Okay? All right, looking over at page 249 in the exercises, these you're solving for x. So they wanted you just to remember how to solve some exponential equations. Exponential equations. We actually did a couple exponential equations when we did difference equations. We had to do some. How would you go about, say, solving problem number, how about 22? How would you solve problem number 22? 2 to the 4 minus x is equal to 8. How would you solve that? Okay, there's two ways you can solve it. Right, you could use, in this particular one, you can get the bases to be the same. So you could say 2 to the 4 minus x equals 2 cubed. And so when you have an equation and the bases are the same, you know the exponents must be equal. All right, what's another way you could solve this one? Yeah, and that's what we had to do with difference equations, where you took the natural log of both sides. Remember that? Take the natural log of both sides, and then what would be the next step? By taking the natural log of both sides, what were you able to do with that exponent? Bring it down in front. So you have 4 minus x times natural log of 2 equals natural log of 8. Okay, and then what would be your next step? Your goal is solving for x. Divide by natural log 2, so you got 4 minus x equals natural log of 8 over natural log of 2. This seems like a hard way to get to this answer, doesn't it? When you could get the bases to be the same, but it's still going to work out. What would be your next step? Subtract 4, negative 4 plus natural log of 8 over natural log of 2. So x is 4 minus natural log of 8 over natural log of 2, and then you just pull out your good old calculator. Let's get this answer over here. What's x1? Okay, so all this work and x will be equal to 1. 4 minus parentheses natural log of 8 divided by natural log of 2. And there's our answer, x equals 1. Check. Okay, so two ways you could solve these equations. All right, and again, this was algebra review. They just wanted to remind you when you're solving exponential equations, you need to get the bases the same. How would you handle problem number 26? Problem number 26. What would you do here? Okay, so you have a product. The whole thing is raised to the fourth. So you could, well, but inside, there's two ways you could go. Inside parentheses, you still have the same base. When the bases are the same, what do? You could add the exponents. So there's two ways you could go here. I would prefer, personally, that inside parentheses, since the bases are the same, I'd write that as 3 to what power? 2x plus 2, and now it's raised to the fourth equals 3, and then now we've got the power of a power, so that would be 3 to the 8x plus 8 equals 3 to the first, and so then you would know x is 1. But what you were saying would have worked just fine. Also, you said I'm going to raise 3 to the 2x to the fourth and 3 squared to the fourth, and that's equal to 3 to the first, so you get 3 to the 8x times 3 to the 8th, and now bases are the same, add your exponents. So either way was perfect. Okay? All right. So the first part was just reviewing of your pre-calculus skills. All right, let's look in the exercises 4.2. 4.2, this was where you got into the natural exponential function. How do you think you would solve problem number 19? E to the 5x equals e to the 20th. Right, the bases are still the same, so you say 5x equals 20, x is 4. Okay, so it's the same kind of algebra review as from the first section. I'm on page 253, section 4.2. Okay, solving, but now you have natural exponential function. All right, then in the last lecture we talked about derivatives, and this was the real hard problem. What's the derivative of e to the x? E to the x. That's why that function is so special. If you know the y value, you're going to know the rate of change, because the derivative of e to the x is e to the x. How would you go about Okay, let's just ask some questions. How would you do number 35? What would you do for taking the derivative here? General power rule. Okay, just tell me what it would be, the derivative. 4 times 1 plus 5 e to the x to the third times 5 e to the x. Is that good? Okay, how would you do problem number 30? What rule? Quotient rule. All right, in general, what's the quotient rule? Y'all go ahead and mumble it. Quotient rule. Okay, so some of you are yodeling and some of you are doing lows and bottoms and tops. All right, so take a second and find the derivative of number 30. Okay, help me. What is it? X squared times e to the x, right. X squared times e to the x. What else?
Oh, you said 32.
Yeah.
Oh, did I say the wrong problem?
32.
Oh.
30 just has an X.
Oh, y'all are just not paying attention. I'm sure it had to be you, not me. What, number 30. Thank you.
Minus x.
Minus. Did I hear a plus?
Minus
It's minus. Okay, minus.
x times e to the x over e to the x squared.
Okay, let's go ahead and simplify this while we're at it. Let's just simplify. What does the numerator factor? How does the numerator factor? E to the x times 1 minus x. And in the denominator, I have a e to the x squared. And what's going to happen with the e to the x over e to the x squared? Okay, so this one divides out with one of those, so it's 1 minus x over e to the x. Are we good? Okay. Tell me what you do in problem number 37. Find the point on the graph where the tangent line is horizontal. Find the derivative and do what to it? Set it equal to 0. You guys are very, very good. Okay, next page. Top. Number 40. Find the slope of the tangent line to the curve y equals x e to the x at the point 1e. How do you find the slope of a tangent line? Find the derivative. Okay, so once you find the derivative, that is the formula for the slope, and you want specifically at a point, so what are you then going to do? Plug in 1 for x, right. Right. And see, they were nice. They gave you the y value, but if you put in x at 1, you get 1 e to the first, so you would know the y value is e, but they gave it to you. Okay? Alrighty. I think you can do it, don't you? Yes. All right, let's go to some homework questions, and we're going to look at some WebAssign questions. Let's see, is the screen up? Here we go. All right, the first homework question that we're going to look at is applications of the derivative, problem number 2. Applications of the derivative. All right. And the question was about problem number 2, wherever that is. Right here? Okay, what part of this question did we have a question about? Was that it? Yeah.
Mine's look kind of different.
Right, yours is different, but which part? Because they should be somewhat similar. I mean, you probably got a different graph than me.
Well, A and E was, let's see. Yeah, A.
Let's see all of them.
Tell you what, let's just go to. Do you care if I pull yours up? All right, because people for years will be looking at your work. Is that okay? I don't want you to sue me. You're okay? I'm going to go directly to your work. Okay, don't y'all look at this. Don't look, don't look, don't look. Till I pull hers up. Okay. All right. So which problem did you have a question with?
Point A and point E.
Okay, point A.
But actually all of them.
Oh, no.
Sorry.
All right. Okay, the question is about, at A, is it increasing? Was that the kind of question that had point A? Okay. So you would say at point A it's increasing. Would you say that's a concave down or a concave up? Concave down. What other kinds of things could they ask? Oh, okay, that's terminology. The function is increasing because the y values are bigger, correct? Now, slopes increasing means the slopes, you know, here's a positive slope, bigger positive, bigger positive. So are the slopes getting bigger? So all around A, you've got a positive slope, but as you're tracing it around, are the slopes getting bigger or smaller here?
Smaller.
They're getting smaller. Anytime you got a concave down, the slopes are decreasing. Concave down, decreasing slopes. Concave up, increasing slopes. Okay? So if the function increases, that just means the y values are bigger. If the slope increases, you're going to have to get a concave up. All right, did that help answer your question?
Yes.
Is that all on that problem?
Not for the last one.
B. Let's B.
Question B?
Yeah.
All right, let's look at question B here. Would the function be the function increasing or decreasing here? Decreasing. Now, to me, that looks like a special kind of point there. What would you say B is? Inflection point. So if it's an inflection point, it's not either concave up or concave down. So therefore, you couldn't have a slope increasing or a slope decreasing. Because an inflection point, the slope is going to change on each side. Does that help?
Yeah, but it's not the answer. It's not complete answer.
Don't look at these answers. The function is decreasing. It is an inflection point, so there's only two answers there. Right? Only two answers. For that one, it's not a slope increasing or decreasing because there is no concave down or up. It's where the second derivative is equal to 0. Okay, it's not a max or a min. It is an inflection point, and there's no concavity there because it's concave down on one side and concave up on the other. So it's just an inflection point, right? But the function is decreasing there. Does that help? Okay, is that pretty good on that one? All right, homework 6. E?
Yeah.
Point E? Okay, that looks like to me that's where we have a horizontal tangent line, right? So that would not be increasing or decreasing there. You got a derivative equal to 0, so at that point it's not an increasing or decreasing. It's an extreme point, right? What's the concavity there? Down. So would you say the slope is increasing or decreasing there? Decreasing. Decreasing slopes means concave down. Does that help? It would be a relative max because in this little neighborhood right here, remember, be around your relatives, it is the highest point in that little neighborhood, so it's a relative max. It's not an absolute max. The absolute max is over here where there's not even a point drawn. This would be probably section 2.1 and 2. Chapter 2, sections 1 and 2, where it uses words to describe, and then it uses symbols to describe. Is that good? Are we good on this one? Okay, thank you for letting me show your work to everybody. Okay, let's see. Oops, I just lost my webassign, didn't I? Okay, well, we had to go to homework 6, so that the next question was on homework 6, problem number A. Homework 6, number 1, A and F. Okay. So, what's the question asking? Where the derivative is greater than 0. The slopes are, the function increases. Function increases. Not slope increases, but the function increases, because it's a first derivative. All right, so the factored form for the derivative is given to you, so you're checking around, what, 1 and 4? 1 and 4. Okay, I'm going to have to do the little sign chart myself. So you got 1 and you got 4. And we want to know where the derivative is positive. So if you pick a number bigger than 4, it's positive, correct? The first derivative is greater than 0. Pick a number between 1 and 4, such as 2, and it's still positive. And less than 1, such as 0, it's negative. Okay, I already know why you guys made a mistake, if you made one, is you wanted to include 4 in your answer, didn't you? I bet you wanted to do 1 to infinity. How many wanted to do 1 to infinity? Why can you not do 1 to infinity? The derivative is not greater than 0 at 4. At x equal to 4, the derivative is exactly equal to 0. The question's asking you, where is it greater than 0? So you have to go 1 to 4. Where is that? 1 to 4. All right, because at 1, it's exactly equal to 0, so that can't be part of your answer. 4 can't be part of your answer because that's exactly equal to 0. So 1 to 4, and then it should pick up at 4 and go to infinity. Okay? Does that make sense? The question is exactly equal to 0. All right, and F on this problem? What's what?
Question.
Okay.
So why can you not do 1 to infinity, but you can do 4 to infinity when the function is a 0 at 4 also?
The parentheses around 4 means the 4 is not included. If you did, that's a good question. It's called interval notation. If you did square bracket 1 to 4, like this means the 1 and the 4 is included. If you use parentheses 1 and 4, it means you're as close to 1 as you can be, but it's not 1, and it's as close to 4 as you can be, but the 4 is not there. So here, 1 and 4 are included. Does that help? Apparently not. Say it again.
Okay, so since on here the 1 to infinity is in parentheses, and parentheses means 1 isn't included.
Right.
Can we select that one?
No, if you select 1 to infinity, wouldn't that pass through 4? And 4 can't be in your answer.
Okay, I got it.
Everybody got it?
Yes.
All right. The next part was number 11. F. 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 Okay, over what intervals is, what's this word right here? Slope increasing. So what are you looking for in the picture for increasing slopes? Concave up. So we want to go look at the picture and see where is it concave up. Oh, we don't have a picture. All right. I'm just on automatic here. I don't even know what I'm doing. All right, so now we're going to go to which derivative for concavity? Second derivative. Second derivative is 12 times x minus 4, x minus 2. Draw our little sign chart, 2, 4. Put in a 10. What's that, positive? put in a number like 3. What's that, negative? Number less than 2, such as 0, positive. Okay, positive second derivative means concave up. Concave up means slopes increase. And here's another concave up, which means slopes increase. So my answer is going to be from negative infinity up to 2, and from 4 to positive infinity. Now, did I remember the question right? F, slopes increasing. So I'm looking for a negative infinity to 2, and I'm looking for a 4 to infinity. How's that? Are we great? It's function increase, first derivative. Slopes increase, second derivative. Okay? All right, the next thing we were supposed to look at is homework 7, problem number 3. Okay. I don't know why I knocked it out just a second ago. Let me log in again. Sorry. Y'all sing a song while I'm waiting. Everybody watching these will try to figure out my password. Okay, so we're looking now at what, homework 7? Hopefully I got it with, okay, and the question is problem number 3. Problem number 3. Okay, I don't know if your numbers are the same or if these are randomized. So if I make it big. Okay. Do you know if the numbers are randomized? You got the same ones? Okay. All right. This one has a little bit more to it, I think, than the problem we did in class yesterday, so we can handle it. What are we going to be minimizing? Inventory cost. So we got to come up with a formula for all the ordering, the carrying, all that stuff. All right, so let's start out. The store expects to sell 800 ovens in a year. Let's let X be number of ovens per order. R is the, what, number of orders per year. So how are you going to translate 800 ovens? X times R equals 800. That's called my constraint equation. Okay. Now let's start getting into our inventory cost. Each oven costs the store $80. These must be toy ovens. Okay, each oven costs $80, and there's a fixed cost of $24 to place an order. So this is the part that's a little different than the example we did yesterday. So let's just do some pretends. Pretend that you're going to place an order and you're going to order 10 ovens. So what's this first line going to cost you? 10 times 80 plus 24. Suppose you're going to order 5 ovens. What's it going to cost you? 5 times 80 plus 24. All right? So to cost to place the order then, so we're going to have a cost to order. Can somebody give me the general formula if X is the number of ovens ordered? 80X plus 24 is the price of one order, right? And how many times a year am I going to do that? R times a year. Does that make sense? It costs $80 times one oven, if you just ordered one, plus 24, and then how many times a year you placed your order, which in our case would be 800 times, wouldn't it, if you just ordered one oven at a time? Okay, everybody got that? Okay. It's easier when I help you, isn't it? All right, then it costs $62 to store an oven for a year based on the average number in storage. All right, so it's going to be $62 for one oven. What's the average number you have in storage? X over 2. X over 2. All right, if it said $62 based on the maximum number you have in storage, it would have been 62x. Okay? Is that good? All righty. What's the problem with this equation? Too many variables. And that represents all the ovens you might want to order the entire year, but we're going to be restricted to 800 ovens. So R is 800 over X. And you just carry it in there. Is that good enough to get you going again on that problem? Okay. There was a question on more on derivatives. More on derivatives. Where is that? More on derivatives number 3. I don't even see that. I must have made it up. More on derivatives. Oh, here it is. More on derivatives. Okay, problem number 3. Oh, yes, a very good question. All right. This is just trying to make sure that you know what the formulas are and what the symbols mean. So we'll do a couple of these together. This is just a drill in formulas and symbols. All right, let me write down f of 2 is 4. Are these your very same problems? Okay, so you got some randomized. I was just trying to decide how much to do for you. All right, let's just do several because we're going to have a good time. All right, just tell me what the first question says to do. What does the first question tell you to do? What do these symbols mean that you're supposed to do? You can't see it. Well, let's enlarge it. Does that help? Okay. So it's basically saying I've got two functions added together. Let's find the derivative of those two functions and evaluate at 2. So whenever you're taking the derivative term by term, isn't it just the derivative of f plus the derivative of g and then evaluate? So for part A, the derivative of a sum, f of x plus g of x, evaluate at x equals 2, you're going to find the derivative of the f, you're going to find the derivative of the g, and you're going to evaluate at 2. So somebody tell me that answer right away. -4 plus 4, 0. Okay? Let's look at problem B. Yeah, it was scary just to look at the way they had it. B says you're going to do the derivative of what? F of x, let me hear it, times g of x. What rule are you using? Product rule. So for part B, you're looking at f of x times g of x, and then you'll evaluate at x equal 2. So the product rule is the first function times the derivative of the second function, plus the second function times the derivative of the first function. And of course we're going to evaluate all these at 2. Isn't it easy when we do it together? Okay, so f of 2 is 4. The derivative at 2 is 4. G of 2 is 4. F prime of 2 is -4. Well, why don't I just go ahead and put 0 down for all the answers? I'm sure they're not, but anyway. All right, does that make sense, everybody?
Yep.
Everybody good? All right, what do you think you're going to do in C?
Quotient.
Yeah, because you heard f of x divided by g of x. Okay, what do you bet you're going to do in D? Still got to do a quotient rule, right? The bottom, the low for you yodelers, times the derivative of the top, right? So you take the bottom just like you see it, which is f of x plus g of x, times f prime of x, minus the top f of x, times the derivative of the bottom, and you're just going to take the derivative of f of x and g of x. Okay, so we try those again? Didn't look quite as bad there. Alrighty, good. We are good. That's the last of the major questions this group had for me. Yes? Homework 9? Let's see where that is. Okay. Which one?
I don't know why, but it might be the way I entered in the web sign, but it's just that first one.
The first one?
The derivative.
Okay. Do you have your work with you?
Yes.
Okay. Do you mind showing me what you put in?
Yes.
Yes, you do mind, or yes, you'll give it to me?
So look here, ignore the rest of that.
Okay, because I figured I knew what your mistake was.
Okay.
All right. This is it up here. Right here?
Mm-hmm.
Okay. Are we on the screen? We are, aren't we? All right, so when you entered e to the x, how did you type it in WebAssign?
Lowercase e times, or lowercase e x, and then open parentheses x plus 1 close parentheses.
Okay, somebody help me.
Just put a, yeah.
Okay, when you're putting in natural exponential function, if you just put in an e, it thinks you're just telling it a letter or something. It doesn't know that you mean natural exponential function. So when you get ready to put in an e to the x, and this is with all mathematical software, you have to go exp parentheses x. Okay, I am so glad you asked me this because people go, I have worked this problem and it's counted wrong. I know I'm right, and it's the symbol.
Okay.
It's the symbol. Okay, thank you. Yeah, this is the same thing as the natural exponential function e to the x. Okay, if mathematical software, any letters you put in, it thinks it's just letters. But we have a special function, the natural exponential function, e to the x. Okay? Everybody good? Thank you so much for asking that.
Wait, so to say EX, wait, is that EX?
E.
How would you?
You got to first take your.
How do you do it?
You have to first take your derivative by the product rule, and when you go to put your answer in WebAssign, did we just? Oh, we did the quotient rule, didn't we? We didn't ever do x e to the x a second ago.
Oh, never mind.
It's e to the x.
Never mind, I got it.
Exp parentheses x just means e to the x. Now what?
So I don't have to put the little raised
There.
to that.
Right, you don't have to do that little caret. Now, if you wanted to type in x e to the x, how do you have to put that in WebAssign and all mathematical software? X times expx. Okay. Suppose you wanted to put in e to the 3x. Exp, probably 3 star x, because you usually have to put in your multiplication. And the new versions of software that comes out, sometimes they'll take care of that for you. And I learned way back in the first version, so I always am careful to put in my times and multiplication. All right, everybody good? Okay, we are ready to get our one last little topic on the test, and you're going to be good at it. All right, and this is going to be your chain rule. Your chain rule. And this will actually go into section 4.4. Chain rule from 3.2 and textbook section 4.4. Oops, it's not 4.4, 4.3. Sorry, 4.3. All right, I left it alone for a while because you didn't see a reason to need it till now. All right, So far, if I give you y equals e to the x, everybody celebrates because the derivative is e to the x. But how do we deal with something like y equals e to the 2x? Okay, we only have the rule for e raised to the variable x, not a function of x. All right, now we can get around this because we know our properties of exponents. So we would rewrite this as y equals e to the x squared. And then what rule would you use? The general power rule. So you would have dy dx equals, you'd bring the 2 down, rewrite, decrease by 1, derivative of the inside. So you would have 2 times e to the x, now raised to the first. The derivative of e to the x is e to the x, and that comes out to be 2 e to the 2x. X to the first times x to the first is x to the 2x. All right, well, that one's not too bad, but how would you have dealt with something like if it were e to the 2x plus 10? All right, so they could get more interesting than this one. All right, so just like when we had a product rule, we needed a new rule, and we need another rule when we have y equals e to the u, where u is some function of x. All right, so I'm going to start a new page, and this is called the chain rule, and then we'll come back to this very same problem. All right, so from 3-2, and we're going to use u's because we need u's once we get an integration. So that's why I focus on the u for the chain rule instead of composition of functions. All right, so the chain rule for this is when we have y is equal to e to the u, where u is some function of x. But we want the derivative of y with respect to x. So the derivative will be, we'll take the derivative of y with respect to u, because y is in terms of u, and then we multiply it times the derivative of u with respect to x. Y is a function of u, u is a function of x, so the chain rule to find dy dx is dy du to u dx. And you can sort of think of those little increments as, you know, just little changes in y's over change in x. They kind of divide out, and that's how you get your dy dx. All right, this looks worse than what it is. Here it is, y equals e to the 2x. All right, because it needed to be an x for the derivative of e to the x, but it's now a function of x, we write this as y equals e to the u, where u is 2x. Y equals e to the u, where u equals 2x. So if I take the derivative of y with respect to u, well, it's just like e to the x, dy dx, but it's dy du, e to the u, so the derivative e to the u is just e to the u. The derivative of u with respect to x is 2. So if I want the derivative of y with respect to x, the derivative of y with respect to x, it's going to be dy du times the derivative of u with respect to x. But your original problem did not have a u in it, so you have to make that substitution back. So it's e to the 2x times 2. That's called the chain rule. All right, still looking bad, but I'm just going to tell you, it's just easy words. And the words are this. The derivative of e to some function is simply e to that function times the derivative of that function. I just needed you to know that, you know.
So we don't have to worry about the rest.
Well, I'm not going to ask you to say, what is the u, what's du, write it out as the chain rule. But it is a chain rule. That's what it is. So the derivative of e to some function is simply e to that function times the derivative of that function. All right? I'm going to flip the page. What is y equals e to the 3x squared plus x plus 2? Find the derivative. Got it? Let me see your work. Aren't you glad you sit on the front row? Okay, let's see if we need to edit anything. Can you see it? There you go. All right, y equals e raised to the 3x squared plus x plus 2 dy dx. That's a good little check. Good notation. The derivative of e raised to a function is e raised to that function times 6x plus 1. Would anybody do any editing to that? You edited your own thing. Yeah, it's times this whole thing right here. Because if you don't have parentheses, it's just the e to the exponent here times 6x, and then you got a plus 1. So be careful with your parentheses. How many left off their parentheses? You're the only one. No, you're not. All right. So e raised to any function is e raised to that function times the derivative of that function. Okay? All right, here's the rule in the book. I'm on page 255. 255. E raised to a function g of x is e raised to that function times the derivative of that function. Or, writing it in terms of u, the derivative of e to some function, e to the u, is e to the u times the derivative of the u part. Everybody good? All right, let's try another example. I'm going to try to think of something hard. Okay, here's a hard one. Y equals 3e to the square root of x. Y equals 3e to the square root of x. Find the derivative. Okay, you got yours? Okay, well, if it's not, we'll fix it. You don't have to worry. Okay. First thing she did was looked at that x to the 1/2 and got the derivative, which is 1/2 x to the negative 1/2. You want to be really careful with your writing. Do you mean 1 over 2 square roots of x? Oh, that is what you meant, right? Remember, the negative exponent means it goes down in the denominator. Yeah. So I thought maybe you were trying to slide that little line like that. I was giving you the benefit of a doubt. Okay. All right, so the derivative of 3e to the square root of x is 3e to the square root of x times the derivative of that square root of x, which is 1 over 2 square roots of x. How is it, everybody? Good? All right, I'm going to show you this page. Pick one, we'll work it, and then we'll call it a day. I want you looking at exercises 4.3. Pick a problem you want to do. I'm on page 258. 258. You don't want to do number 1. Tell me, everybody, what the answer to 1 is. So 4e to the 2x times 2. What's the answer to number 2? Say it loud. 0. Why is the answer to number 2 0? It's just a constant to start with. All right, so pick one. Let's do it together.
10.
Number 10? All right, number 10 is good. Oh, would you like your paper back? Okay, together, problem number 10. This is page 258, and the problem is g of x equals e to the minus 2x minus 2x raised to the third. All right, tell your neighbor the process, and then we'll do it together. What are you going to do?
This is general power, right?
Yeah, we're doing the problem. Okay. This is retarded.
Okay, what rule are you starting out with? General power rule, because you don't really care what's inside parentheses in the beginning. You got a 3, and then you're going to bring it down, rewrite, decrease by 1, and then worry about the inside, right? So we're starting out with the general power rule. We brought the 3 down. We rewrite exactly, decrease by 1. And now we're going to multiply, don't forget your parentheses, derivative of the inside. E to the minus 2x, the derivative of e to the minus 2x is e to the minus 2x times negative 2. Most of the time you usually put that in front of your e, just looks better. So the derivative of e to the u, where u is a function of x, is e to the u times the derivative of the u. Okay, now what's the next part? Minus 2. Are we good? Check. Well, that didn't take but a second. Do you want to do one more? We still have another minute. Okay, question, yes.
So if we have like e to the minus 2x, can we bring that in the denominator if we
Yes,
wanted
the
to?
question was, could you bring that in the denominator? You could write that as negative 2 over e to the 2x. Yes, because,
Negative 2 is the whole entire.
right, e to the minus 2x is e to the 2x to the negative 1 power of a power, so you get 1 over e to the 2x. Okay, did I hear a 12? Oh, man, 12 is easy, easy, easy. All right, let me rewrite number 12, and you'll say, that is so easy. That is basically number 12. Let me show you number 12, if you don't happen to have your book here. It looks ugly, but it is easy. It's e raised to the minus 2x squared plus 2x plus 1 all over 10. That is the very same thing as just saying 1/10 times e to the minus 2x squared plus 2x plus 1. It's a constant times it. Right? Divide by 10 is the same thing as 1/10 times. All right. Make me feel good. What's that derivative? 1/10 e to the minus 2x squared plus 2x plus 1 times plus 2. All right, so what made it look bad was the 10 was underneath. Divide by 10 is the same thing as multiply by 1/10. So that's what scared you. And did you say number 14 looked bad?
Yeah.
No, it does. It does look bad. I'll agree. All right, number 14. G of t equals t squared. And how would you write that 1 over t? Can you write that to t to the negative 1? Right. So it'd be e t to the negative 1 power. Would that be better? All right. What rule are you going to... Let me hear you say this. Say it. T squared times... So you know you're using a product rule. All right, let's go with the product rule. The first times. Now, what is the derivative of e raised to some power? E to that power times the derivative of that function, which is what? Negative 1 t to the negative 2, right? A t to the negative 1 is the same. T to the negative 1 is 1 over t, right? So when you take the derivative of t to the negative 1, you're going to bring the negative 1 down, rewrite, decrease by 1. And derivative of t is 1. Everybody good on that? All right, so there's first times derivative of second, and then the rest is e t to the negative 1 times 2t. All right, so let's just clean it up a little bit, and then we'll be good. Let's see here. How do we want to deal with that? A t squared times a t to the negative 2 when the bases are the same. Add the exponents, right? So t squared times t to the negative 2 is t to the 0, t to the 0, which is 1. 1 times negative 1 is negative 1, so you got minus 1 e to the 1 over t, 1 over t. This little part right here, 1 over t. Just trying to make it look pretty. All right, and then the next part is plus 2t e to the 1 over t. Question was, what happened to those t's up there? When you have t squared times a t to the negative 2, bases are the same, add the exponents, t to the 0, which is 1. Okay? Everybody good? Yes?
But one not a negative and another is positive. The sign are different. The t squared and negative 1t squared.
Well, I kept the negative 1 right there. Right. Okay, I have just run 2 minutes over. Have a great weekend, everybody. I'll organize your questions for Monday. Organize your questions. Your test stops at 4:03. Stops at 4.3. Could what be reduced to? No, you can't add those. They're not similar terms. There's a t in there.